Hi there. I'm Łukasz. I usually say I'm from the internet, but Poznań is not so far this time around. So I'm from Poznań. You can come visit when we finish our renovations, which we're hearing is really soon now. We'll see. You can find me on the internet. I'm pretty responsive, I think. Used to have a Twitter link there, but I still have a Twitter handle. You can also talk to me right there. I'm sponsored by the Python Central Foundation. I work for them directly. You can also be a member, which would be a really nice way for you to actually have influence over where Python is going. You can vote on PSF board, elections, and so on and so on. So I invite you to look into becoming a member of the Python Central Foundation, which would be a way for you to actually feel like this is also your programming language. Today we're going to be talking about generators. We're going to be talking about what the point of them is, of thinking about how generators are stranger than most of your other tools in the Python toolset because they're bidirectional. You can communicate with them. We're going to be talking about how they are a building block of coroutines, and then how you can actually use asynchronous generators in Python as well, and a little bit about the future, or like where we can actually go from where we are today. So let's start at the very beginning. So the point of the generators. For most of us, generators have always been there, but they've been added to Python in 2.2 in 2001. So over a decade of the existence of Python was without any form of generation. So the details are described in PEP 255. This is a form of generators that is more basic compared to what we have today. So let's just go ahead and see how a generator looks. So the point of a generator function is that it decouples how values are produced from how they are consumed. From the perspective of the consumer, it works as a simple iterator from which you can get values one by one. In this case, we're just calling next on the generator. And note how the generator protocol is using an exception to denote it's done. We're not saying none, we're raising an exception because none could be feasibly a valid value that the generator is giving to the consumer, right? So it's very rare for people to actually call next on generators. More often, you would have iteration over it. So you would use the for loop, but the for loop here is only syntax sugar over the calls that we saw in the previous example. So the exception is still raised by the generator, but it is handled by the for loop itself so that it knows it's over, we should break. So from the perspective of the generator function, however, you can produce values using a logic that can be complicated and even non-linear, as well as to keep complex state that you need between the values that you're yielding. And that is the power of the generators, that it might not appear to the consumer that the logic inside your generator is in fact non-trivial. So on top of the function syntax, there is an expression syntax for generators too. It's especially useful for trivial generation. It's preferred over list comprehensions because it allows composition of multiple layers of generation. And when you're iterating, computation only happens on an as-needed basis, so just in time. The details of that is in PEP 289, so that is one thing that was added after the original generators were introduced. And the implementation landed in Python 2.4, so at this point I was already a user of Python, so I remember when this was new, like it was a long time ago, but yeah, like I was excited. Okay, now like we're gonna be able to be more lazy in our computation. So now, it might have been somewhat abstract to you when I said, oh, the point of generators is decoupling how values are produced from how values are consumed. So let's look at a more, like illustrative example then. So here you can see a function that is called getResults, and it composes a list of results that are calling some expensive operation. For our purpose, the simulation of the expensive operation is just to sleep for a bit. But you can imagine any sort of computation that takes a non-trivial amount of time. So at the bottom here, I'm using rich progress to show a nice progress bar that, you know, we're actually going ahead with our computation. And when you try to execute this, you will see that it is a little disappointing. You don't actually see any progress, you know, just the cursor is just stuck there until the get results function is done. And only then you just saw the entire thing appear in one fell swoop. Not really a great experience. So now let's replace get results with gen results, right? So in this case, this is almost the same, only we're yielding results of the expensive operation one by one. And the call to reach progress is essentially the same, only we replaced get with gen here. So when you actually run this, that gives a much more pleasant experience. We see a progress bar, we see values appear as they are produced. The code itself doesn't run faster, but the result is more interactive, more informative. So more importantly, this uses way less memory because you don't have to accumulate all results before we get to act on them. So the consumer deals with a result as soon as it's available. That's more efficient. Better yet, our latest for loop could itself be part of a generator. So creating a composable, lazily computed design. And this is, by the way, how Black is implemented internally. So now, let's actually see how we can influence what a generator can produce. Let's say we have a generator that connects to Redis and one by one yields messages published on some channel. Of course, this is potentially an infinite loop, but we all know nothing is really infinite in computer science. At some point, we will want to break out of this loop, either by an explicit break instruction or by Control-C, so by raising the keyboard interrupt exception. So this is a reasonable thing to expect on the consumer side, but it gets somewhat gnarly on the generator implementation end. So on the implementer end, we have state, some of which is remote, the subscription to a channel on Redis, and we have some logic to only return some data that's interesting to us. So to clean up after yourself properly, we need to use try finally, so that we always unsubscribe and we always close our connection. So while this code is simplistic, you would probably not want to use this in production. Like, it is correct. Like, you could see in the previous example, it actually will show us some results like coming from Redis and so on and so on. But it doesn't really explain what Python does exactly when the consumer puts a break statement in the for loop. So to just see that mechanic, let's use a synthetic example just to see how Python functions internally. So here you can see something that just yields to values. There's a try finally like we had in our previous example, and we're printing whether there is any current error, so any raised exception right now that wasn't handled yet. So when we exhaust this generator fully, we see there's no exception being raised, which is why the xinfo is none, none, none. Sure, the generator itself later generates stop iteration, as we saw in the very first code example, but that's only after the generator function returns. So here, none, 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 no exceptions. However, if we break the iteration early, the generator sees a generator exit exception being thrown inside by whom? By the consumer side. So the user is talking to the generator. What might surprise you is that this wasn't possible on day one when generators were first added. This came 4 years later in PEP 3.4.2, which is maybe surprisingly named coroutines via enhanced generators. Well, wait, this isn't async.io yet, and this isn't about async generators yet. Those are plain old generators described here, but enhanced with the ability to send information to them from the user end. So let's focus on that bit now, and we'll get back to actual coroutines later. So when the consumer breaks the for loop prematurely, Python internally calls a method on the generator called close. This in turn uses another method on the generator called throw to raise a generator exit exception inside the generator. So the throw method allows for throwing arbitrary exceptions, but generator exit is special, right? Because it's used internally by Python to stop generators that are no longer needed. So let's test this method on an example. Another super trivial example, we're going to have a print before and a print after, and inside there's a try except block yielding just a single value. When there's an exception, we're going to say there was one. So now, after we consume a value yielded from the generator, we throw an exception and see how the try except block nicely handled that exception, led to the generator body to finish, and the generator returns, which raises stop iteration. Cool. What if it had more things to yield? So let's modify this to have another yield after the try except. So now if we run this, the throw method continues the generator until the next value is yielded. So when the generator handles the exception, it can continue running and yielding values. So calling throw really potentially returns values. Let's look at the original example again. When a generator is instantiated, it doesn't execute anything just yet. Therefore, if we call throw on a new generator like this, the exception is raised before the first line even executes. So let's see this in action. And note how there's no before printed out, and the generator is no longer in a usable state because it raised exception that wasn't handled. There was no try except here, like it couldn't really handle this. It didn't run any code internally, so it bubbled back to the user. But what if we don't want to throw exceptions into generators, but just pass on regular data? Since like with throw and with exceptions, you could imagine constructing some, weird machine that actually passes data into a generator, but it would be very cumbersome to actually write code like this. So we don't want to use throw, we want something easier. So fortunately, there is a better way. And now, it's kind of boring to have all those super synthetic examples, so let's go and talk about something real for a second. I like real-world examples because they feel more grounded to me. I feel like, why is this useful? So let's talk about mini audio for just a minute. This is a library that allows you to process streaming audio in real time in Python. Think about this again. Like, it uses generators to process real-time audio. So audio rate processing that you can do. You can, synthesize new sounds. You can process like adding delays or whatever else. This is actually now with current processors and current computers like fast enough that you can pull it off in Python. So I successfully used this, in fact, to make a Yamaha DX-like frequency modulation synthesizer. That's essentially the sound of the 80s. So if you want, you can watch my PyCon US 2021 talk about this. For now, the only thing you need to know is this one detail about how mini audio works. So in general, digital audio works on a stream of numeric values, right? So each one of those values is a sample of the amplitude of the sound at that particular moment in time. So when you emit the stream of numbers into an analog output like a speaker, you will hear sound. In this case, you will hear a sine wave, right? So in the ideal world, to actually make this work in a computer, when the audio loop works in an operating system, the operating system would ask for a single audio sample, which is a single number. Then mini audio would call next on our generator that would produce a single number in Python code. Then the generator in turn would yield that single numeric value after doing whatever computation it needs. And then mini audio would pass this one single number back to the operating system. So that would be sample precision audio processing. That would be amazing. Sadly, this is too slow in the real world. Operating systems are very busy running hundreds of processes, and Python code, maybe it's too slow to actually do this in a reproducible manner like all the time, since if you couldn't keep up and you wouldn't give that number just in time for it to hit your speakers, you would hear clicks and pops. You would hear that, the audio isn't really produced at the rate it should be. So in the real world, what you have is we work with buffers of many samples. So this ranges from anywhere between 32 samples on production audio interfaces all the way to thousands, when that introduces latency between when you want some computation to happen and you hear the result, but you can work with that, right? So ideally, mini audio would work with those buffers, but internally in our code, you would still have a generator that generates per sample, right? That would make our code kind of simpler to think about. That would make everything kind of elegant implementation-wise. But it turns out that it's still too slow for Python because, you know, audio level processing, where stereo audio is 44,100 samples per second per channel. So you would have to run our generator 88,200 times per second to actually get the values just in time so we could play them. So instead, many audio uses a trick where it tells our generator how many samples it wants in advance, right? So just give me 128 or 768 or something. And then you would generate that in one fell swoop with NumPy or the built-in array module in Python and so on, and pass that, right? So it turns out that this is fast enough for the entire system to work and for Python to process audio in real time. And to the end user, the latency is the same. So essentially, it's only a little complication that we have to introduce when we are coding some audio processing in Python. So how does many audio tell the generator exactly how many samples it needs? Well, instead of calling next on the generator, it calls a method called send with an argument that is the number of samples it wants. And then the generator yields back an entire array of the length that we wanted into a buffer, right? So how does the generator see this inside the generator's code? In fact, this is all kind of Matryoshka, like, you know, generators all the way down, so we can look at the implementation of this particular function because it does the same. The generator sees the thing that was sent to it as the return value of the yield expression. Yes, with PEP 342, yielding became an expression that returns values. So the code you see here is actual code from the FM synthesizer that I mentioned before. So it's a generator that transforms monophonic signal, so an array of just, you know, amplitudes in one channel, into stereophonic signal by panning it somehow. So, you know, you can either have it in your left speaker or in your right speaker or somewhere in between. So as you can see, it is a generator itself, and it is processing another generator's output. So as I said, like, you know, it composes, which I find very elegant. So the only weird thing about this is that there is already code to be executed before we got our first send, right? So like we already, to actually get the value back from the yield, we need to do the yielding first. So what should we do? In this case, we just send the entire buffer like until some max buffer value at first, and only later we trim it once mini audio tells us, actually, don't send me 1024, like just send me 256 or whatever. That's a little mind-bending at first, but you know, you can get used to the strangeness of generators. Like maybe let's look at this in a simple example. So here we have another super synthetic thing where there's a print at the start, and then we yield 1, we get a value back, we print out what that value was, we yield 2, get a value back, and then print out what that value was. So on the consumer end, if we try to send to the newly created generator right away, Python will object. It will say that no, you can't send non-none values to a just started generator. Instead, you need to call next or send none, which is the same, you know, as the first operation. So let's do that then. As you can see, our generator now yielded its first value first, even before we ever sent anything to it. So yielding happens first, and when we sent the first string, it correctly said it's the string returned by the first yield, and then immediately yielded the second integer. So this is a little bit of a disconnect here that, you know, kind of you can maybe misunderstand from just reading the code. It takes a moment to understand that when you have this yield 1, right, you yield it first, but nothing was returned to the generator just yet. The value in the first yield returned from the user is only passed when we're running code that gets up to yield 2, right? So it's a little bit shifted then from, at least I would want it to have, like I would want it to look like, but it's something that we have to live with. So you don't really have to always think about this detail. Usually it just works fine. But every now and again in debugging, you would see this off by 1 when you thought that the value passed by the consumer is being passed a little sooner than it actually is. But this in particular enables asynchronous communication between a consumer and a producer. And between multiple generators if the consumer actually orchestrates this somehow. So this is the basis of how coroutines were originally implemented in Python. So let's talk about that for a minute. So in fact, Tim Peters noted that generators can be a building block towards coroutines as early as July 1999, long before even generators were added to the language. It sure does sound smart and convincing, but what does he really mean here? How are generators implemented so that when the current state of each coroutine is contained in a single frame, it's really no harder to implement than generators. So let's see how they're actually implemented internally. So to understand generators, we need to understand functions and frames first. So we've seen this function already, right? You see, when you write a function in Python, you create a template of code that can be executed later. So we understand that this code isn't executing right there and then. You need to call it first. So in fact, Python allows you to see what that template is using the dis module, dis standing for disassembler. So this reveals that the function has been compiled by Python from text source code into bytecode. And I don't expect you to understand this right part if you haven't ever seen opcodes. The actual point is just the bird's eye view, that a function is essentially a template, a code object that allows it to be executed later. So things get more interesting when you call that function, because this function has some state, right? It has some state that includes local variables. So you need to store it somewhere, and you cannot store this state on the code object directly, because the same function can be called multiple times at the same time. For example, by recursion, so when the function calls itself, or if you have threads, you can have the same function running on multiple threads at the same time. So they will have separate state. They will have different values of the variables that we see in the code. So we cannot use the code object to store this state. Instead, we use what we call frames. So let's see frames in practice. So let's look at our trusty function again. The point of it really is this expensive operation inside. So let's tap into that function and look around. So what you can do in Python is you can start an interactive interpreter using code.interact. So it'll just start a REPL. In this case, it starts a REPL within a REPL, which I find a little funny. So let's run this get results and see, kind of what happens inside. So we start a get results with how many set to 1. And now we can actually import sys and run our trusty get frame function. So the first frame is going to be the frame of the interactive REPL that we have here. So by the time we get to some frames below this, you're going to see the implementation of code interact. And it only takes us before, you are smoother doing the actual live coding than I am with this animated GIF. So, okay, I wouldn't try animated, live coding on my presentation. So get frame 4 already is code interact, and by get frame 6, we see our expensive operation, and get frame 7 is our get results. So we can look at that frame closer, assign it to a value, and now we can see that it has a bunch of attributes. And one of those attributes is f_locals, which stores our local variables. So we can check that how many is indeed set to 1. So what we essentially did is we traversed the stack of frames so we can demonstrate this call stack in graphical form. So first we had our REPL, then we called get results of 1, which created a new frame on the stack that in turn ran our modified expensive operation, that ran code interact, and finally we got to our internal REPL where we could interactively create new code and get it to execute. So that's why we needed to say sysgetFrame of 7 to get all the way back to get results and to see the local variables of that. So right, when we close the internal REPL, that frame will go away. And in turn, code interact with close. So that will result in expensive operation to continue, which returns the random number that we had in our implementation. And then we're back in get results of 1, which takes that returned value and puts it in a list and appends it and returns the list. And finally, we're back at our REPL console. That's why we're talking about this as the call stack, right? So generators use the same idea. They use the frame, only it's not tied to a call stack. It can just live in an arbitrary life cycle. So essentially, it's a long-lived object that you can consume values from at will. So we saw simple generators before, but you might have not known at the time is that they in fact have a code object inside them, and they have a frame inside them when they're running. So a running generator has this frame and that we can inspect. So we could, for example, try to see whether the val equals 0 here, which is the first line in the generator before any yield, is actually set in the locals correctly. And if we do, maybe that surprised you. Value is not bound yet, and the reason why we didn't call next for the first time, right? So before that generator actually ran any code, those locals are unbound yet. But as soon as we do call next, we're going to see that in fact the locals are set to the right value. We can already see that value because it was returned from the generator, but we really wanted to check that the internals of the generator represent the same thing. So enough calls to next, we will reach the end of the generator. So right, like that way we actually have the frames that we can hold onto. And that is essentially Tim Peters's insight. We can hold on to frame objects for generators, and if they can hold state, we can just as well use that for cooperative multitasking, in other words, for coroutines. But there was one more step that we still needed in the evolution to allow this. So we needed two things that were added in PEP 380 that landed in Python 3.3, so a long ways away from all the other generator PEPs. The first off is this yield from syntax that allows consuming an iterator in one expression. So we say delegating to another iterator because, kind of from the perspective internally of Python, for a while somebody else is being iterated from, but kind of from the perspective of the user, it's not much dissimilar from a for loop where you're just yielding one by one from some other iterator. And the second thing that we needed, that was a crucial addition for async.io later, is the ability of a generator to return a final value. That was just implemented as an attribute on the stop iteration exception that we already had. So you'd think that yield from is just syntactic sugar over this for loop I mentioned, but in fact the truth is way more complicated than that. Like, I don't expect you to read this tiny code, I just put it on a slide to demonstrate that because of close, throw, and send that we already talked about, as well as generator exit, as well as stop iteration, with stop iteration now having a value actually, the actual equivalent Python code for our 2-line for loop is 40 lines long actually. There's a lot that happens there. So now we are where we are today, right? We have this generator that allows you to yield values, but also be sent values to it. You have yield from, where you can delegate to another iterator and actually get some value returned from it finally. You have next, also known as gen send. In fact, you have send, right? Like, which is generic to be able to send to a generator. You have throw, you have close, and the two exceptions that we talked about, like one of which implements returning a value from a generator. So a pretty, kind of powerful piece of functionality that we have in the language. So one note. You might have noticed that I annotated some of the functions with types before, and I used the iterator annotation and not generator. So what was that? Well, from the perspective of the user, what you're getting when calling a generator is an object that provides a dunder next method, so can be iterated on. In other words, that is essentially what the generator does when it's simple. When you're not sending anything to it, when you're not returning any final values, when you're just yielding, this is equivalent to any other sort of iterator that iterates values. And the reason I prefer this vague iterator annotation is that the actual annotation for generator contains all those three pieces of information: what it yields, what can be sent to it, and what the final returned value is when it exits. So this is useful when the generator actually does all those advanced things. But when you're not doing it, you know, in my kind of for my taste, it's a little too verbose. I just don't like it, like to have to specify all those nuns that are kind of spurious to me. So what I actually do when we have verbosity like this is often I would add meaningful aliases to types that otherwise are some rather complex thing. So this is why you've seen audio before, but what that really means is a generator that yields audio buffers and that accepts unbuffer size sent to it. We already saw in the implementation that this is what was happening, but I guess with those annotations, that is more clearly a human, readable thing. Like it expresses the intent of the programmer. Right, so let's finally get to async I/O, right? This is not a place where I can, do an async I/O primer. So if you came here for that, like, I'm sorry, like the time slot is too short, like that's out of my hands. So I have an entire talk series about, async I/O, so you can watch that. But let's just say Tim Peters was right. And thanks to generators being regular Python frames, you can use await to suspend execution of one and execute another coroutine to execute. So one example that I like to give, even though we don't really have time to talk too much about async I/O in general, is this. You have async functions now, so async defs, and you can await in them. In this particular case, the awaits come one after another. So downloading the second file will only start when the downloading of the first file is finished. So this is essentially something that is, kind of understandable for regular Python code, which I find really nice about async I/O, that you also read it from top to bottom. But you can do a little magic, and now those three downloads happen concurrently. And this is the power of cooperating multitasking, powered by coroutines. And I like this example a lot because it also shows how all of those things compose, because it's a real working example. The only thing you need is an implementation of get one. So let's look at one. Here we go. As you can see, this is ripe with async context managers. So there's a bunch of lines here. And why do we have those async context managers? Because in Python, what very often we need when we're dealing with asynchronous programming is some sort of connection or transaction. So something that we establish, we do a thing, and then we disconnect. Or a transaction that we start, and then later we want to commit or roll back, and so on and so on. So asynchronous context managers allow us to nicely wrap this with the enter and exit operations happening implicitly, so we don't have to think about them every time. This is kind of elegant in terms of how it looks to the user, but internally, it is almost the same thing as a regular context managers, only now you don't have enter and exit, you have a enter and a exit. The difference there being that they are coroutines now, so you can await inside them. So you can actually establish an asynchronous connection to a database, or you can, do whatever that you need asynchronously. So similarly to asynchronous context managers, we have asynchronous iterators that allow you to iterate over some abstract thing that needs to sometimes await, right? And it may be called to the network and so on and so on. So that, again, has equivalent of dunder iter and dunder next with a iter and a next, which are now coroutines, so they can contain await and await expressions inside. Right, so what if we actually tried to use a generator in the old world anyway? So the oldest version of Python that I could run on my Mac now is 3.5. Yeah, there's 2.72, but that doesn't have any async IO. So yeah, like from the 3 versions, 3.5. So originally we didn't have async and await keywords, and none of those async iterators, async context managers. We had this very bare bones, maybe hack or kind of clever use of decorators that just reused existing generators in Python to work as coroutines. So you had to decorate a function or like a generator function with asyncio.coroutine so that asyncio could know what to do with it, that this is going to actually be a coroutine. So there could not be anything in asyncio or Python at that time that would stop you from just adding some random yield to your coroutine code. And if you did that, obviously that wouldn't work in practice. You would get an exception. And the terrible thing about it is that this is a very cryptic exception. Like you don't know what task it got a bad yield. You don't know where from because that's nowhere in the stack trace. It wasn't a good time at that time. I was early adopters of asyncio, like they had to go uphill both ways. So Python 3.5 actually brought the async and await syntax, and with that there were the additions of async iterators and context managers and so on, and coroutines became their separate objects just so that we could catch all those errors where people would be yielding from something that wasn't a coroutine or yielding something inside a coroutine, which at that point wasn't possible yet. We couldn't have this. So maybe that would be enough, right? Having async iterators and async context managers. So what's the big deal about introducing async generators? And why did we have to wait for that later? So asynchronous generators that were added in PEP 5.2.5 in Python 3.6 were a ton of work. They added the dunder next and send, throw, close equivalents that are asynchronous, so with the A at the beginning. And now there are coroutines, which I find is the most important thing. That now all of those functions can have awaits inside, so you can do operations that are potentially asynchronous and long and reach to the network and so on. So this is an example straight from the PEP. The async generator implementation here looks straightforward enough, right? You have some transaction that we open with a context manager. Then there's a cursor for our database. We have an async iterator that we go through, and we yield a value that has some computation added to that, right? On the consumer side, it doesn't look any different than any other async iterator. And that's because it is an async iterator, only async generators are way more powerful because now they can easily store state and they read like any other piece of Python code. So you should already be able to recognize that there's this complication on the user side, right? Like before, we had break in regular generators and that was fine. But now when we break in an async generator, what we actually need to do is we need to run this exit code that will roll back our transaction. So the event loop of asyncio needs to be able to still keep running even though the code here already broke, and maybe that's already exited asyncio, like maybe there's no longer anything asynchronous happening in our Python process. So how does Python know that there's still some cleanup that is asynchronous and the event loop has to continue running? So that had to be added to the language itself, to the interpreter itself. And this is this hook that we have here that allows you to finalize any async generator that is about to be destroyed by garbage collection. And that is not even the most complicated thing that we got when async generators were added, because while asynchronous generators look to the user like regular generators, and you can use them based on your experience with regular blocking generators, the implementation required a shadow rewriting or re-implementation of how sending and throwing works. And the reason why is that while coroutines are now separate objects, they still have the same send and throw APIs. So you had to actually have something that mimics regular generators on top of the coroutines that we have. I will spare you looking at the PyAsync Gen async implementation right now, since I'm slowly running out of time. Plus, we actually have like a bunch of complicated edge cases added on top of the thing that landed in Python 3.6. So now it's no longer so welcoming to the first time aficionado, but you can believe me, like, kind of, it's gloriously complicated. It's something that, kind of takes a while to understand. So maybe more high level. What's the big deal about async generators? Why you should be using them? So my personal opinions of like the top 3 reasons for this would be that modeling producers as async generators is often more elegant than creating an explicit producer-consumer queue. And that avoids back pressure, actually. So like if you haven't never heard the term, like back pressure is like resistance opposing the desired flow. So if you would have more values produced than you're able to consume, at some point the queue would get full because, kind of there would not be, balance between the producer and the consumer. So in the case of async generators, the producer always produces just the amount of data that the consumer is ready to process, and that is really elegant. The second thing would be that if there is a connection to be made and later disconnected, or a transaction to be open and later committed, our instinct is to use context managers. And in async generators, that is still true. The context manager would be moved into the generator implementation. But the nice thing about this is that now the consumer of this doesn't have to think about opening all those resources and cleaning them up. Even if that's just one line of the context manager, like they sum up and they steal our precious indentation levels. So, kind of it's just more elegant to bundle them inside an async generator. And maybe this third one is just a bullet point for the hardcore async.io users who already wrote some custom async iterators. And if you have any under your belt, you know that any non-trivial async iterator is a nightmare to implement because the state that you want to store between your dunder next calls has to be attributes on an object and so on and so on. Like it's not very easy to see what the current state of the iteration is. So async generators, way less verbose, way more readable. So it feels less clumsy, it feels more Pythonic. So now, this is where we are today. Are async generators done? Kind of, but by now I hope it's clear that the sister implementation of asynchronous generators is complex. So yield from is pretty complex in its own right, as we saw, like 40 lines of Python, right? And it just kind of simulates this 2-line for loop, right? So therefore, so far we haven't grown yield from support inside async generators yet. Maybe some inspired mind here will come and like submit a PR to Python with that, and then we could have async.io implemented inside async.io, and how crazy would be that? Well, all right, that's all I have. My name is Łukasz. I'm here all day, so I'm happy to answer any questions like, at the venue. And if you don't catch me here, catch me on GitHub or Mastodon or email. Thank you very much.
Thank you, Łukasz, for your comprehensive dive into async generators in Python. Fortunately, it's recorded and we may get back to it later because it was really complex, compressed.